This is Kyle Jensen here, and this presentation is a whirlwind tour of computers and software, and it's basically 50% stuff that you should vaguely understand because it provides context on this course. That is, you should understand what do we mean when we say we're developing software, who is developing, for what purpose, where does it sit in the technology stack, and it's 50% stuff that you should understand because it's critical to this class and to your future careers as managers in technology, and I will do my best to leave it ambiguous as to which 50% is which. So, computer chips are built from semiconductors. A semiconductor is essentially a material which has electrical conductivity between that of a conductor, such as copper, or something you would find in a wire, and that of an insulator, such as glass, right? So one transfers electrons, the other doesn't. A semiconductor is semi, right? It's between a conductor and an insulator, so it's a semiconductor. And semiconductor materials can be shaped into transistors, which amplify and switch electronic signals and electronic power. That is, they store ones and zeros. So you can either have the semiconductor material shaped into a transistor that has the current flowing, which means electrons are moving, okay, or not flowing. And so this stores a 1 or a 0, a true or a false. And you make a CPU by using a bajillion transistors, and the CPU performs the basic arithmetic, logical control, and input-output operations of the system, okay? So a CPU is built out of transistors, which are made from semiconductors, and the CPU is stuck onto a motherboard, which has all sorts of other stuff stuck onto it, okay? And all these components are wired together in the back, and those things there you see there in this slide, those are tiny wires, right? And so there's a bunch of other stuff too that goes on top of a board, and memory, expansion slots, USB, Ethernet, all this kind of stuff. So here's a little board, and you can see it's got all these peripherals. It's got an IDE connector, a DRAM memory slot, 20-pin ATX power connector, CPU, fan, heatsink, whatever. And the CPU sits into that little CPU socket, okay? You stick it right on top. And these things come in all shapes and sizes, okay? Your computer has a board, your phone has a motherboard, your toaster probably has a motherboard, okay? So here's the standard ATX, micro ATX, mini ITX. There's all sorts of different boards, and this is just a sampling based on the ATX and ITX form factors. So one of the chips holds the BIOS, and this is also called the firmware. And what the firmware does is initialize the hardware. It loads up the operating system, which lives on the hard drive, okay? So it has these instructions loaded onto it that tell the CPU how to control the various stuff that's attached to the motherboard, okay? So how, and you can see here, how do we control the CD-ROM? How do we control the zip drive, and so on and so forth. This is obviously a very old screenshot because I don't think anybody living today has a zip drive. The point is that the CPU needs to know how to control the things that are on the motherboard, and all that is stored in the BIOS. Now, the operating system sits on top of the BIOS, and there are many different operating systems out there. The majors are Windows, BSDs, Berkeley Source Distribution, and the various Linux flavors. Here you see this fancy penguin here. That's typically the Linux icon, and various FreeBSDs. I'm a big fan of FreeBSD. I love that. And of course, Mac OS X, which is based on FreeBSD. Indeed, all the operating systems that you use today are based on something that probably has a 20, 30, 40-year history. So you can look and see Windows XP came from Windows 2000, which came from Windows 95, and so on and so forth. And you can see the lineage of all these things, right? That you can trace their history back to operating systems that were written many, many years ago. So, with rare exception, your life will be about these parts of the stack. This is the technology stack. There's hardware. Okay, so hardware, we describe the CPU and the motherboard and the firmware. And on top of the hardware lives the operating system. Okay, so that's like FreeBSD or Mac OS X or Windows or Linux. And on top of operating system runs applications, and is the applications with which the user interacts. And so today we'll talk a little bit about these other parts, but for the most part, if you are writing software, you're going to be talking about the user and the application. Very few people do anything associated with the operating system or below, okay? Now, applications are pieces of software designed for a particular purpose, and they depend on the operating system for access to system resources and hardware. So here's all sorts of different applications. The ones in the top left run iOS. The ones at the bottom left are on my Mac, and then top right on my Windows machine. And these are all things that users interact with, right? Well, all these things constantly need CPU, memory, file system, network. They need all sorts of stuff, right? So when you load up Excel, it needs access to the RAM because it needs to store stuff in memory. It needs to store all those numbers. It needs to do computations when you run the solver. And it is the operating system which delegates the allocation of resources that are physically present at the machine to these various applications, okay? Because these resources are necessarily limited and need to be distributed in a wise fashion. And that is the primary role of the operating system. Now, I showed you some apps that you're probably familiar with, but these are just some of the apps. For example, on my Mac, there are many other applications which you probably never see that don't have, for example, icons. This is some of the applications that live in on my Mac in the user bin directory. There's things like tar, which makes a little archive of files, and there's what else is here? Alias, which makes I believe, an alias of a file. Let's see here. Probably dmessage is there, which shows me a dump of, are you there? No. Dir name, okay. Dir name shows me the directory name Python 2.7, which shows me which runs Python. All sorts of interesting stuff here. Tail, which shows me the end of a file. Talk, which allows me to talk to other users on the system, and tidy, which cleans up an HTML file. Time, which shows me the current time. All sorts of applications that you can run using the command line interface, okay? And so a summary of this is that your computer has a bunch of programs or applications that let you play Angry Birds or whatever it is, and by asking the operating system for resources, and the operating system was started by the firmware, and the firmware is stored on the motherboard and a little chip, and the motherboard's heart is the CPU, okay? The CPU is what does all the numerical computation. The CPU is made up of transistors, which are made of semiconductors. So you should have absorbed all that and understand pretty much exactly how your computer works now. Right? Now, programs are run by loading the machine code into the CPU. Machine code is actually just ones and zeros. That's specific to every kind of CPU. So there's many kinds of CPUs, right? There's an Intel Core i7. There's the A6 processor that's in your iPad. There's an AMD 64, Intel Pentium D, whatever it is. And each of these behaves in a different fashion. They each have transistors that are located on them in different places and arranged differently. And the manner in which they execute instructions and perform computation is by basically flipping ones and zeros, okay? And so ones and zeros are sent into these, into the CPUs, and that string of ones and zeros is called machine code. Now, few humans can read or write machine code, so every CPU manufacturer creates a flavor of assembly, a language called assembly for each of their CPUs. And assembly is shown on the left here and gets translated into machine code. So, for example, this is some assembly for the Motorola 6800 processor, right? And this gets translated into machine code, which then gets executed on top of the CPU. Now, few humans actually can write assembly either, and fewer still want to because it's pretty nasty. So we have something called higher level languages, and these higher level languages get translated into assembly, which gets translated into machine code, which gets executed on top of the processor. And you've heard of these higher level languages. So, for example, Ruby, Python, Perl, PHP, Java, Haskell, Clojure, Scala, Go, JavaScript. In this course, we're going to be using a lot of JavaScript. So essentially, higher level languages abstract away the stuff that is a total pain in the butt and lets you focus on the task at hand, which is awesome because it makes you highly productive as a developer. And all these applications here, for example, that I showed previously are written in one of these higher level languages. They are compiled from a higher level language into the machine code to produce your executable, or what's called a binary, okay? And that's what actually gets executed on the CPU. Now, web browsers are a very special kind of application in that they interpret HTML, CSS, and JavaScript that other people write. And I want to talk to you about how special this is. So your web browser requests something from a web server. So here's a browser on the left, and I have the Chrome. It's on my laptop, and I request this image from Imgur, and the web application server sends back this image, which is of this very relaxed cat getting some kind of like top tier cat therapy treatment. And so there's this request and response cycle. I request this URL, and the web server responds with this image, okay? Using a protocol called HTTP. So what is this HTTP? You probably use this every day, but I bet that 50% of you don't know what it means. Here's this guy's tweet here. It says HTTP at the beginning of the URLs is a command to the browser. It stands for head to this place, followed by 2 laser gun noises. Pew, pew. Which is clever, but actually not true. The computers communicate mostly using TCP/IP, and HTTP is part of the TCP/IP stack. So you see at the top left here, HTTP. There's all sorts of other protocols that you probably recognize as well, like FTP and Telnet, and you've probably heard of SSL. And those are at the top of the stack. So that's essentially what computers are talking about. If you go to the bottom of the stack, you'll see things you probably also recognize, like Ethernet and ISDN or wireless or cable modem, and that's how you talk. That's how your computers talk to each other. The IP layer is who you're talking to, so you've probably heard of IP addresses. TCP is essentially what language the computers are speaking, and the fourth level of the TCP IP stack is essentially what you are talking about, and HTTP sits there. In this class, we're only going to be concerned about HTTP. You should understand that computers have multiple kinds of ways in which they can communicate with each other. Okay, so let's talk a little bit about HTTP. Here is a standard HTTP request. I have my browser on the left-hand side. I'm going to request gmail.com. So my request goes to the server, which is sitting on the right-hand side, and Gmail's server, okay, which is an application that's running on computers at Google's. You know, I'm sure there's a server in Sergey Brin's office, and it receives this request and sends back to us some HTML, CSS, and JavaScript, and this gets used by our browsers to produce this Gmail application. Right? You notice that Gmail doesn't feel like a web page, right? It's not just some piece of static content. It's interactive, and that's because there's not only HTML on the page, but there's CSS. So HTML is essentially the content, right? HTML. You see, I have some emails here from Jorge and Jennifer and other people, and that's the content. And the CSS is what the web server sends to us, and that's what tells the browser how to display the content. What font should it be in? What color should it be in? Should that compose button be red? And the JavaScript that the server sends us tells our browser how the application should behave. So what should happen when I click on the compose button? What should happen when I click on that Gmail link? Should it go to a different page? Should it load something different? Should it make a pop-up? Should it archive an email? What exactly should happen? So these are the three components that the server sends to our browser that our browser interprets, okay? So essentially, Gmail is sending your browser a bunch of code, and your computer runs their application, right? They're sending you an application, and your computer runs it. I mean, that's an amazing thing. So they can push updates 24/7, right? There's no user download like you would have to with Adobe, right? There's no critical update to Adobe. When Gmail gets updated, Gmail just gets updated, right? It runs on any device with a browser, and your browser keeps the app in a sandbox, which is to say that applications written for the web don't escape the web browser. And so this is essentially the web as a platform, right? And that should absolutely blow your mind, because what it means is that you can push an application to different people's devices, all sorts of different devices, any device with a browser in a way that is completely fluid, right? It doesn't require them to re-download anything. And increasingly, web applications now have almost a native feel, which is to say that applications you interact with within the browser, they feel like an application that you interact with on your desktop. Now, in this class, we're going to write a web application, and we'll learn the technology, and we'll write a legit application. And essentially, it's going to be of the nature of Gmail, except not nearly as sophisticated. So we will teach you how to write an application, or write a server, rather, that sends back HTML and CSS and JavaScript to a browser and creates a little web app that people can interact with. And that's essentially that's it. That's what the class is about. This is the application that we're going to develop in the class, and we're going to use this application to teach you the technology associated with this, which you're likely to employ in your careers, and also the modern management tools for software development. So we're going to teach you Agile, Scrum, and all the tips and tricks you need to know for managing a team of developers in the production of a software product. So a web app is a program that runs on the server, accepts requests from browsers, and sends back custom HTML, CSS, and JavaScript, as I said in the previous slide. Okay, so here's a little bit more detail on that. The user in the top left interacts with a browser. Okay, the browser requests data or pages or whatnot from a server. The server stores the data, stores information, stores my email, performs business logic. So if I do a search for emails that contain a particular string or a particular reference, a particular person, the computation is done on the server, and the server sends back to the browser HTML, CSS, and JavaScript. HTML is usually the content. CSS is how tells the browser how to display the content, and JavaScript tells the browser how the content should behave. And then the browser displays this to the user. And so the client is the browser. So when we say we have a client-server architecture, we're talking about the client, the browser as the client, and the server as the server. And the client basically stores data locally and performs business logic locally. Okay, it's the thing that the user sees. And this kind of client-server architecture is ubiquitous, right? So the whole web is built on this. There are many people that are constantly connected to Gmail, and they are, you would say, a bunch of clients connected to a single server. But in Gmail's case, it's obviously a server farm, which is to say many servers. Now, servers can be written in almost any language. They're just an application. It's running on this machine that lives somewhere in some data center, or as I said, Sergey Brin's office. And in this class, we're going to build a server application using JavaScript. Now, the client is built on 3 web technologies. So the server part can be built using anything. Clients in the web stack are always built. Well, not always, but for the most part, for your intents and purposes, always built using these 3 technologies. The HTML, which, as I said, describes what content is in the app. For example, this header, this paragraph, these buttons. The CSS, which describes how the app should look. So, for example, this font, this color. And the JavaScript, which describes how the app should behave. So, for example, do this when the user clicks and do this when they search. Now, our server, as I said, will be written in JavaScript too, okay? So we are going to use JavaScript on both the client and the server. And that's a great thing, right? Because then we're not learning 4 languages, we're just learning 3. So yes, you can use JavaScript on both server and the client. And to do that, we're going to use node.js, which is a server-side JavaScript environment. So normally JavaScript runs in your browser, right? It runs in Safari, it runs in Chrome, it runs in Internet Explorer half the time, or with some probability. You can also run JavaScript on the server side using Node. And so Node is just a way of executing JavaScript code on a computer that outside of the context of a browser, okay? And JavaScript, because of its ubiquity, and that is it can be executed in any context, any browser, and now on the server side, is incredibly popular. It's wonderful. I can't say it's the best language in the world, and there are a lot of people don't like it, but the fact is it's ubiquitous, right? So here's this, Who Wants to Be a Millionaire? What's the most popular language in the world? French, Spanish, English, JavaScript. Pretty sure the answer is D. So those are the technologies we're going to use in the class. Now you should have a good understanding of how computers are built, how computers interact with each other, and how applications run on computers, and exactly what we're going to do in this course, which is build a web application, okay, which is a server which responds to requests from a client and presents the user with all sorts of interactivity and data by transmitting HTML, CSS, and JavaScript. So here's how we'll learn these things for this class, Management 656, at the Yale School of Management in spring of 2015. HTML5, or HTML, we're going to learn in homeworks 1A and 1B, and by screencast. You're going to read some stuff, that is to say, you're going to learn this on your own. CSS, we're going to learn in homeworks 1A and 1B, and by screencast, that is, you're going to learn it on your own. And JavaScript, we're going to learn in homework 2, and by screencast, and a little bit in lecture. So we're going to help you out a little bit more with that one. Now, this is a lot to ask, but we have assembled for you best-in-class resources that will help you learn these things, I think, in an expeditious fashion. And also, as you are already aware, the class includes numerous screencasts and lectures like this that will help you with the most technically hairy parts of the class. So that is the lecture, the whirlwind tour of technology and applications.